In this video, we are going to discuss Chapter 4 revision quiz. So I've already handpicked 8 questions that some of you mentioned you have problem with, and we are going to go through these 8 questions one by one, starting with question 12 over here. So the Earth behaves as a magnet with magnetic field pointing approximately from the geographic which pole to the geographic which pole. Okay, so there's two kinds of pole that you need to be careful about. One is the geographical pole, one is the magnetic pole. So these are two different kind of poles. So let's look at this diagram to understand it better. So if this is our Earth, right, we have our Antarctica on the South Pole and we have our Arctic at the North Pole. Okay, so that North Pole that we usually say it's actually the North Geographic Pole, means by the north side of the whole Earth. Okay, so the South Pole where we have our Antarctica, it's the South Geographic Pole. It's the south position of the whole Earth over here. That's geographic based on location. Okay, so north, this is like our compass. We can take north to, this is, I don't want to say compass because compass is related to magnetic. Okay, but for now you just need to know your north, south, east, west is north, south, east, west, right? So this is the north, south, east, west that you're usually familiar with. Okay, that's geographic pole. It's based on location. But if you look at the magnetic field, right, we'll notice that the magnetic field lines for Earth always comes out from the South Pole and it will comes into the Earth from the North Geographic Pole. Okay, it will comes out from the South Geographic Pole and it enters the North Geographic Pole. Again, geographic pole is location. It's not relevant to the magnetic field. Just that it happens that coincidentally, the magnetic field lines comes out from the South Geographic Pole and enters the Earth at the North Geographic Pole. Okay, we learn from our study of magnetic field that the magnetic field lines always come out from the North Pole and always enter the South Pole. So because the magnetic field line is coming out from here, so this should be the North Pole. Then this point where your magnetic field line is coming in is called the South Pole. But since this is related to magnetism, this is called the magnetic pole. So this is the North Pole, but it's a North magnetic pole. If you look at it based on magnetism, then this is the North Pole, this is the South Pole. And actually there's a bit of angle between them. You can see that the North Pole, North Geographic Pole and the South magnetic pole is not exactly aligned to each other. There's a little bit of deviation here. Okay, but what you need to notice is that the North Geographic Pole is around the same side as the where do we write it? The North Geographic Pole is on the same side as the magnetic South Pole. Okay, so if you look at it from a magnetic perspective, right, this position over here is the magnetic South Pole, but it's the North Geographic Pole. On the other side over here, this is the South Geographic Pole. Location wise, it's south, but based on our understanding of magnetism, this is the North Magnetic Pole. It's the magnetic North Pole. So when you talk about pole, you have to be careful whether you're talking about geographic pole or magnetic pole. These are two different things. The North Geographic Pole is the magnetic South Pole. The South Geographic Pole is the magnetic North Pole. Okay, how do we know that all the magnetic field lines are coming out from here? How do we know that all the magnetic field lines are entering the North Geographic Pole? We can know it by compass. By putting our compass at anywhere around the Earth, we will see that our compass will be pointing, our red needle here is always pointing towards the North Geographic Pole. That's why we call that as the north side of the Earth. Okay, the north needle is always pointing towards the North Geographic Pole, but we know that this compass here is always aligned. It's always pointing in the direction of the magnetic field lines. You can see that all the compass, no matter where I put, the needle is always pointing along the magnetic field lines. And because of that, we can make a conclusion that once we trace this line over here, we know that it enters this position of the Earth. So this will be the magnetic South Pole. And where the magnetic field lines comes out is called the magnetic North Pole. Okay, conclusion. North Geographic Pole is the magnetic South Pole. South Geographic Pole is the magnetic North Pole. So as you can see here, the Earth behaves as a magnet with magnetic field pointing approximately from where to where? Magnetic field always comes from the south geographic pole and it enters the north geographic pole. So this time is from south to north. So this is the answer. Okay, next question. An electron and a proton are entering at 90 degrees into a uniform magnetic field with the same speed. Both charges experience magnetic forces, which are initially, okay, so now they ask about the magnetic force initially. Initially means by the magnetic force when the electron and the proton just enter the uniform magnetic field. And it enters the uniform magnetic field at 90 degrees with the magnetic field with the same speed. Okay, so let's try to draw the situation. So let's say today our situation, we have a uniform magnetic field represented by these crosses over here. Okay, and we have an electron and we have a proton. Electron and the proton. I'll use a red pen to represent a proton. A proton is entering the uniform magnetic field at 90 degrees. So you can see the magnetic field is pointing into the page, and my proton is moving to the right. So moving to the right and pointing into the page is 90 degrees to each other. So I can label it like this. Okay, so this one I'll label it as the magnetic field B. Okay, my electron, I think, is also entering at 90 degrees as well. So we'll write an electron that looks like this. Okay, okay, so this is the V of the electron. Okay, they are entering with the same speed, so the V magnitude for the electron should be the same as the V magnitude for the proton. Okay, so let's write it up here. Vp is equals to Ve. They both have the same magnitude. They are both entering at the same direction, I think. Okay, so they are entering with the same speed. Okay, both charges experience magnetic force, of course, because it's a moving charge in a magnetic field. Moving charge in a magnetic field, the moving charge will interact with the magnetic field. As a result, the moving charge will experience a magnetic force. Okay, so now they ask, when they just enter the magnetic field, how do you compare between the magnetic force of the both charges? Whether they have the same magnitude or they have the different magnitude, whether they have the same direction or they have opposite direction. So let's try to determine that. So for the magnitude, you know that the magnitude of the magnetic force can be determined using QVB sine theta, but the Q, you have to modulus it because there can be positive charge, can be negative charge. We want the magnitude, we don't want to consider the direction. So in this case, the sign of the charge is not relevant here. Okay, it's just QVB sine theta. So they tell you that it's a proton and an electron. So you know that for proton and electron, they have the same magnitude of charges. They are both 1.60 times 10 to the power of negative 19 coulomb. So they are the same. You know that they are entering the same speed as well. So this is same. You know that they are entering the same magnetic field. So B is also the same. They are entering at the same angle. So these are the same. So all four of these are same. So you should expect the magnetic force experienced by the proton and the electron to be the same. Okay, so they are equal in magnitude. So if you see differing in magnitude, you can cross it out. Okay, differing in magnitude, then you can cross it out. Okay, so let's look at the direction. Direction, you know that the equation is F is equals to Q V cross B. So the V cross B over here, it's a cross product. So when it's a cross product, you can use right hand palm rule. Okay, right hand palm rule to determine the direction of the force. Okay, so for right hand palm rule, your fingers, you have to be pointing along the direction of the velocity. So in this case, your fingers should be pointing around here. Okay, fingers looks like what? Fingers looks like this. Okay, roughly like this. Okay, so this is my fingers. The four fingers should be pointing along the direction of the velocity, and the palm of your the palm of your right hand should be pointing into the page along the direction of the magnetic field. So you see that the direction of the thumb will be the direction of the magnetic force. So this is a positive charge, so your magnetic force will be along the direction of your thumb. So in this case, the direction of magnetic force will be pointing upwards for the proton, force experienced by the proton. Okay, however, if it's a negative charge, if your thumb is pointing upwards, you have to flip the direction of your thumb to be in the opposite direction. Then that would be the direction of the force experienced by the electron. Electron is a negative charge, you have to flip the direction that you find. So in this case, it's the force experienced by the electron is pointing downwards. So you can see that these two forces here are opposite in direction. Okay, so your conclusion is they have equal magnitude. Why do they have equal magnitude? Because proton and electrons have the same magnitude of charge, and they are moving with the same speed into the same magnetic field at the same direction. So everything Q, V, B, and theta are the same. Okay, the direction wise, because they have different charge, then this Q over here can be positive and negative, then you flip the direction. Okay, I won't go too much about the equation. I'll just use right hand rule to explain it. So we have mentioned just now, using right hand rule, if it's a negative charge, you flip the direction that you find. That's why it's in the opposite direction. Okay, so it's equal magnitude but opposite direction. So from our discussion right now, we can immediately take our answer as B. Okay, this is very similar to your individual assignment question. Okay, so this is how you should explain the whole situation. Okay, next. Question 21. A current loop is oriented in 3 positions relative to a uniform magnetic field. In position 1, the plane of the loop is perpendicular to the field line. Okay, in position 2 and 3, the plane of the loop is parallel to the field as shown below. Okay, so you have 3 different orientation over here. In position 1, the plane of the loop is perpendicular to the field line. So how to describe it is like, if this is your plane, right, then your magnetic field line is passing through the plane perpendicularly. So this is your plane of the loop, then your field line is perpendicular to the plane of the field line, the plane of the loop, sorry. So that is position 1. So if you flip it like this, then your plane of the loop is like this, then your magnetic field is passing through like this, perpendicular 90 degree over here. Okay, in position 2 and 3, the plane of the loop is parallel to the field as shown below. So this is the plane of the loop. If it's parallel, then that means the direction of the field is parallel, something like this. Your plane is in this direction, so it can be in this direction, it can be in this direction, it can be in that direction. But in this case, position 2, the magnetic field is crossing like this. It's crossing like this. In position 3, it's crossing like this. Okay, no matter what is parallel to the plane is flat, then the magnetic field is also along this plane. Okay, so position 2 and position 3 are quite similar. Okay, the torque on the loop is maximum in which position? Position 1, position 2, position 3, or position 2 and 3. So this is the question they're asking for. You know that torque in a loop, the equation, okay, if you refer back to the vector equation, the torque equation is torque is equals to Ni, and you have your A cross B. Okay, then after that, if you break open it, then you get the magnitude to be Ni AB sine theta. Okay, so you know that in order for your torque to be maximum, maybe I shouldn't write like this. For torque to be maximum, your sine theta must be equals to 1. Okay, so sine theta equals to 1 means by your theta must be equals to 90 degree. Okay, then only your torque max will be equals to NIAB. Okay, so what does it tell you? This theta here is the angle between A and B. Okay, so what conclusion can you make? Angle between A and B should be 90 degree to get what? Torque maximum. Okay, so let's try to figure out which one will have wait for a while. Okay, so the torque should be maximum if your area vector and your magnetic field is 90 degree. So let's check which one fulfill this situation here. Area vector should be perpendicular to the plane of the area. Perpendicular to the plane of the area. Okay, so in this case, if you look at position 1, right? Position 1, this is the plane. Okay, this is the plane of the area. So perpendicular to the plane of the area means by you have to be either pointing in this direction for your area vector or pointing in that direction for your area vector. Okay, so we can take our area vector to be pointing in this direction, pointing like to the right out from the plane. So in that case, you can see that your magnetic field B and your area vector A are pointing in the same direction. And because they are pointing in the same direction, the angle between them should be 0. In this case, your sine theta will become 0. So in this case, your torque will be equals to 0. Okay? Let me double check. Yes. Okay. B. Page B. E. Yes. Okay. Okay, so let's look at position 2. Position 2, your plane is now placed like this. They place the plane like this. So in that case, your area vector will be either pointing out of the page or pointing into the page, depending on which direction you choose. So in this case, you can simply take one direction. I can put the direction of the area vector to be pointing into the page. As long as it's perpendicular to the plane, then it's okay. So I put it to be pointing into the page for my area vector. And my magnetic field is pointing to the right. So one is pointing into the page, one is pointing to the right. The angle between them is 90 degree. Okay, it's 90 degree between them. So theta is 90 degree. Okay, so this one, your torque should be maximum. Okay, let's look at position 3. Position 3, they lie down your book flat, like, I mean your current loop flat like this, and they have your magnetic field pointing to the right. Okay, so your area vector is either pointing this way or pointing this way. No matter what, it should be perpendicular to the plane. So let's pick upwards as our direction here. So I'll pick upwards as the area vector. Definitely area vector should not be so should be straight, perpendicular. So let me draw it once more. Okay, so this is your area vector and this is your magnetic field. Theta is equals to 90 degree once again, so your torque will be equals to torque max. Okay, so position 2 and position 3, they both have torque maximum, so our answer will be D. Okay, if you check for yourself, right, you go try, let's say you have current. Okay, if you're not sure whether you're right or not, that's how I checked just now. You try to put in a current into the loop, then you try to determine the direction of the magnetic force. Okay, if you have current flowing upwards, and you have current flowing upwards, then you have magnetic field pointing to the right, then you see that your magnetic force will be pointing towards the center. This one will be pointing towards the center. The magnetic force will be both pointing into the center. So they will cancel each other out, so there will be no torque. Okay, but in this position 2 over here, if you try to let the current flow inside this current loop, then you see that one of the force is pointing into the page, another force is pointing out of the page. So in this case, it will cause the current loop to rotate. Okay, this one is similar. If you try to make a current flow inside here, then you will see that one side you have force pointing in this direction, another side you have force pointing in this direction. Okay, so it will cause the loop to rotate this way. Okay, in this situation, it will cause the loop to rotate this. One is down, one is up. So it rotates this way. Okay, so that's the situation where you have maximum torque. Okay, so that's all for this question. Let's move on to the next one. Question 22. A magnetic field is directed out of the page. So you can see over here, these circles with dots over here are representing magnetic field that are pointing out the page. Okay, the two charged particles enters from the top and take the path shown in the figure. So path 1 here, it's one of the charged particle moving in from the top. Path 2 is another charged particle moving in from the top. And this is the path that is shown in the figure. So now they ask which of the statement is correct. Let's try to see what kind of statement do they want you to verify, and from there we determine how should we solve the problem. Okay, so they ask whether particle 1 is a positive charge, particle 2 is a negative charge, both particles are positively charged, negative charge, positive charge. Okay, so they are mostly concerned about the sign of the charge. Okay, unless you pick D. If you pick D as your answer, then it does not depend on the sign of the charge. But we know the direction of the path depends on the sign of the charge. We learned that in the our right hand palm rule to determine the direction of the magnetic force. Okay, so the idea is like this. If you have a charge entering the magnetic field and it shows a path that is curving in this direction, then you know that if there's a large region of magnetic field, you trace out a circle like this. Okay, so if you trace out a circle like this, then you know that the centripetal force should always pointing towards the center of the circle. Therefore, you should expect the magnetic force on this charge should be pointing to the right. Okay, FB1. Okay, let's look at the second particle on the right. The second particle on the right, if you trace out the whole path, imagine you have a very large uniform magnetic field, then your circle will be something like this. Okay, in that case, the center will be on the right of this path, so therefore you should expect your magnetic force to be pointing to the right for particle 2. Okay, so now the question is, how do you create a force that is pointing to the left? How do you create a force that is pointing to the right? Remember, the magnetic field are all pointing out of the page. So when you use your right hand rule, if you want to get if you use your right hand rule, right, and you have your, okay, let's mention the speed as well. Okay, the charge is moving in from the top, so of course your speed, your velocity for particle 1 is pointing downwards, your velocity for particle 2 is also pointing downwards as well. So you have determined the velocity, you have determined the you have the magnetic field, you have the magnetic force, you have everything already. You just need to see if it follows right hand palm rule, then it's a positive charge. If your magnetic force is opposite of what your thumb shows, then it's a negative charge. Okay, so if you use your right hand palm rule on particle 1 over here, your forefinger should be pointing downwards, then your magnetic field should be pointing out of the page. Okay, this is mine pointing out of the page. Mine out of the page, fingers pointing downwards. Then my thumb is pointing to the left. So my thumb is pointing to the left for particle 1. And my force in the diagram is also pointing to the left for particle 1. So that means that my direction of magnetic force follows the direction of my thumb. So if it follows the direction of my thumb, then that means this is a positive charge. Okay, then let's move on to path 2 over here, particle 2 over here. Particle 2 over here, the direction of the velocity is also pointing downwards, so my fingers is pointing downwards as well. Then after that, I know that the magnetic field is pointing out of the page, so my palm of my hand over here, my palm is pointing out of the page, Okay, so if I'm pointing out of the page, then my thumb will be pointing to the left. Okay, the thumb is supposed to represent the direction of the magnetic force, and my thumb should be pointing to the left. So that means if it's a positive charge, the direction of the force is pointing to the left. If it's a negative charge, the direction of the force should be opposite to the direction of my thumb, which is to the right. In this case, in my diagram over here, my force is pointing to the right, which is opposite the direction of my thumb. Therefore, it shows that this is a negative charge. Okay, so therefore we can say that particle 1 is a positive charge, particle 1 is a positive charge, particle 2 is a negative charge, particle 2 is a negative charge. So this is the answer. Do you know that they cannot be both positively charged? Because if both positively charged, then they both curve in this direction. Okay, you can see that this will be curving in this direction if it's a positive charge. Okay, particle 1 has negative charge, particle 2 has positive charge, then it will become curved like this. You curve in the opposite direction, and D is incorrect because we know that F is equals to Q VB. Okay, so the direction depends on your right hand palm rule over here. And this Q here, because it has positive, it has negative, then this one you follow the direction of your thumb. Negative, then you flip opposite the direction of the thumb. Okay, so these are the things that you use to understand how to determine the direction of the path. Okay, I want you all to know that right hand palm rule, right, there's different kind of right hand palm rules. Some people prefer the fingers to be pointing in the direction of the, I don't know, they have different versions. For me, I follow the version that is in Young and Friedman University Physics. But of course, right hand palm rule, there's various versions. Okay, so if you hear this version of mine is different from what you see in your books, it's just because we have different versions. It's not because I am wrong or he is wrong or what. Okay, just different. Okay, so that's it for this question. Let's move on to the next one. An electron moves into a uniform magnetic field with a certain velocity. If the velocity of the electron is in the same direction as the magnetic field, which statement about the motion of the electron in the magnetic field is true? Okay, so let's try to draw the situation over here. So you have an electron. Okay, an electron. Let's draw E minus over here. And it moves into a uniform magnetic field with a certain velocity. So let's draw a certain velocity to the right. So this region here is going to have a uniform magnetic field. Uniform B. If the velocity of the electron is in the same direction as the magnetic field, okay, they are providing some clue about the direction of the magnetic field. It's the same direction as the velocity. So you can draw your magnetic field to be pointing to the right as well. Okay, so I label this as B. Okay, so now they ask which statement about the motion of the electron in the magnetic field is true. So they ask whether the electron will accelerate or the electron will decelerate, or whether it will continue to move with the original velocity, or whether it will move in a circle with constant speed. Okay, so if we look at the situation over here, we know that we can try to determine the magnitude, we can try to determine the direction like usual. Okay, so the magnitude over here, we know that it will be F equals to the Q of the electron V B sine theta. Okay, the theta over here will be the angle between the velocity vector and the magnetic field vector. Okay, it all comes from this equation here. Okay, if you break the V cross B over here, then you get VB sine theta. Okay, so this equation here tells us something about the magnitude. It also tells us something about the direction. Okay, I've written this a few times. Direction is V cross B. You use your right hand palm rule. Then if it's positive, then you follow the direction of your thumb. Then if it's negative, it's opposite the direction of your thumb. Okay, so let's try to determine this. Okay, let's try to determine the magnitude first. We know that the magnitude is Q VB sine theta. We know that Q for electron is negative 1.60 times 10 to the power negative 19 coulomb. But since there's a modular sign around it, then you don't need to introduce a sign inside. Okay, the V is not known, the B is not known, but never mind, let's just leave it like this. But when we look at sine theta over here, we look at the angle between V and B. The angle between V and B are in the same direction. So if V and B are in the same direction, that means that we don't really need to substitute everything in. We can keep everything as it is, but when we sub in sine theta, theta will be 0. We know that sine 0 degree, the answer should be just 0. Therefore, the magnitude should be equal to 0. That means there is no magnetic force acting on the electron. Okay, if we have no magnetic force acting on an electron, and in this situation they don't mention any other kind of forces, so we can come up to the conclusion that there is no net force over here. Okay, sum of F is equal to 0 because there's no other force and there's no magnetic force as well. So in this case, you can reach the conclusion using sum of F equals to ma. You can say that the acceleration is equal to 0. So because you know the acceleration is equal to 0, you know it won't accelerate, you know it won't decelerate, because that means acceleration is not 0. But in this case, the acceleration is 0. And if you see it move in a circle with constant speed, you know this is uniform circular motion. Okay, if you know this is uniform circular motion, you know that you need centripetal acceleration. And if you need centripetal acceleration, then that means you need a centripetal force. So in this case, there's no force in the first place. There's no force acting on the electron right now. So it's impossible you have a centripetal force. Okay, the centripetal force will be the magnetic force. If there is a magnetic force, then it will be the centripetal force. But in this case, there's no force acting on the electron. So there'll be no force that can be acting as the centripetal force. So there'll be no centripetal acceleration. So there will be no uniform circular motion to be found. So this is wrong as well. So you can see that it's moving with its original velocity. So this is just Newton's first law. Okay, first law says that if there is no net force acting on it, so it will remain in its state of motion. So initially, if it's moving with a certain velocity, it will continue to move in the same velocity, same magnitude, same direction, not changing direction, not speeding up, not slowing down. So that is what will happen if the net force is equal to 0, which is the case right now. So this is how we slowly analyze the situation to determine whether there's any acceleration. If there's no acceleration, you should expect constant velocity motion. Okay, so that's it for this question over here. Let's move on to the next one. A plotting compass is placed near one end of a solenoid. So you have a plotting compass over here. You can just call it a compass, and it's placed near one end of the solenoid. In this case, it's placed near the end Y over here. Okay, when there is no current in the solenoid, the compass needle points as shown. So right now, the compass needle is pointing towards the north side of the diagram. The north side of the diagram is pointing upwards, and the compass is pointing upwards. Okay, so now when the current flows in the solenoid from X to Y, the magnetic field produced is of the same magnitude as the magnitude of the Earth magnetic field. Ooh, so many magnitude. Okay, so the idea is like this. When there's no current flowing in the solenoid, the compass needle is pointing like this. So when there's no current flowing here, there's no magnetic field produced by the solenoid. So right now, if this compass is pointing in this direction, this is only influenced by the Earth's magnetic field only. Okay, there's no other current around the compass, so there's no other sources of magnetic field near the compass. So in this case, the only magnetic field that influences the direction of the compass is the Earth's magnetic field right now. Okay, so this direction is the direction of the Earth's magnetic field. Okay, so let me draw it here. The direction of the Earth's magnetic field. Okay, so now when a current flows in the solenoid from X to Y, the magnetic field produced is of the same magnitude as the magnitude of the Earth magnetic field. So later, you will have another magnetic field, which is called the magnetic field produced by the solenoid. And it should have the same magnitude as the Earth magnetic field. So you should expect these two arrows to have the same length, but this B solenoid here will not be exactly pointing in the same direction as the Earth's magnetic field. It will be pointing in the direction that we need to determine now. And once we know the direction of the magnetic field produced by the solenoid, we can merge with the magnetic field produced by the Earth, and from there we can determine the resultant magnetic field, and we know where the direction of compass will be pointing towards. Okay, now of course the question asks the compass then points to which direction. Okay, so what we need to do now is we need to determine the direction of the magnetic field produced by the solenoid. That's our first step. Then after that, the second step will be merging it with the magnetic field produced by the Earth to find the resultant magnetic field. And from there, you know where the compass will be pointing towards. Okay, so how do we determine the direction of the magnetic field produced by the solenoid? We look at how does the current flow in the solenoid. So we know that the current flows from X to Y. So if we trace out the diagram, you see that it's down, up, 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 down. Okay, so this is the direction of the magnetic field, the direction of the current flowing in the magnetic field. Okay, so right now what you can do is you can use your right hand grip rule. Okay, you can use right hand grip rule to determine the direction of the magnetic field produced by this solenoid current right now. Okay, and how do you do it? Using right hand grip rule. Oops, my right hand grip rule. Okay, so your current is flowing exactly like what I show here, I think. Yeah. Okay, your current is in front of the tube. If you imagine there's a rod inside the solenoid, in front of the rod you have your current flowing down, and behind the rod you have your current flowing up, down, up, down, up. Okay, so this is similar to the diagram that we have over here. And if we use our right hand grip rule, we take our fingers to curl around the direction of the current. So the direction of the current, if you take your rod, right, if you take your rod, your hand, your fingers at the back should be pointing up. In front of the finger should be pointing down. In front of the finger, your current is pointing down over here. current is pointing down in front of the rod. Behind the rod, the current is flowing up. So behind the rod, flowing up, in front of the rod, flowing down. So this is how you should grip your finger. So once you grip it properly and you point your thumb, you see that your thumb is pointing to the right. Okay, you have to look based on this diagram. The camera might be flipped direction, I'm not sure. But this is how your hand should look like if you do it properly. Okay, so from this right hand grip rule over here, we are able to determine that the direction of the North Pole is pointing towards the right hand side. Okay, so you can think of the situation here as you have created a magnet where the North Pole is pointing in this direction, the South Pole is in this direction. Why do I say you can think of it as a bar magnet? Because later when you try to determine the magnetic field of the solenoid, the magnetic field lines of the solenoid, you can see that the magnetic field lines of the solenoid will look something like this. Okay, forgive my drawing, it's all freehand. Okay, this is all inside the solenoid. My skill is not so good, I cannot do all the front back thing. But this is how it roughly looks like. So you know that North Pole, all the magnetic field are pointing out from the North Pole and they are coming in from the South Pole. Okay, so if you extend this line over here, you know that the magnetic field is pointing to the right over here. Okay, so from this diagram over here, we have determined that at the compass position over here, the magnetic field, you have another new magnetic field that is pointing to the right. Okay, so this is the magnetic field that is produced by the solenoid. And this is the magnetic field that we originally have, okay, by the Earth. We say just now, the Earth is pointing outwards, and now we have determined the magnetic field produced by the solenoid to be pointing to the right. So that means if we place a compass over here, if this is our compass, and this is our compass needle, then later you find that the compass should always be pointing along the direction of the resultant magnetic field lines. Okay, so your magnetic field, once you merge these two magnetic field, you find that the resultant magnetic field is pointing in this direction. The B resultant is pointing in this direction. Therefore, you should observe your compass needle to be pointing in this direction. Okay, so this direction is over here, and this is northeast. That's why the answer is A. Okay, so this is actually similar to the experiment 4 on magnetic field, which we never really do it face to face, or like we never really go discuss it, but the idea is similar. You have an existing Earth magnetic field, but you create an external magnetic field to change the direction of the compass. Okay, feel free to look back at the lab manual for experiment 4. It's the same idea. Okay, so because originally you have the Earth magnetic field, therefore the compass is pointing towards the north. Then after that, by introducing a current into the solenoid over here, what happened is you introduce a magnetic field that is pointing to the right. So combining the magnetic field pointing upwards and the magnetic field pointing to the right, you'll find that the resultant magnetic field is pointing in the first quadrant, which is the northeast direction. And therefore, your compass needle will follow the direction of this magnetic field over here, and therefore your compass needle will be pointing in the northeast direction. So that's how you solve this question over here. So next question. Two long parallel conductors are separated by 1 cm and free to move. A current of 20 ampere flows in the same direction in both conductors. The conductors, they ask whether they remain stationary or they move away from each other, or they move towards each other, or they rotate in a clockwise direction. Well, this should be a quite straightforward question, but let me visualize the situation first. So you have two long parallel conductors. So I'm drawing one. I'm drawing a second one. Okay, so these are two long parallel conductors and they are separated by 1 cm. Okay, and they are free to move, means that we are not fixing their position. They can be not separated by 1 cm later. Okay, right now it's 1 cm, but after that when they move, then they can be separated by any other cm. Okay, a current of 20 ampere flows in the same direction in both conductor. That means that inside both of the conductor, you see current flowing, and this is 20 ampere, and you have current flowing here, then this is 20 ampere. Then they are both in the same direction. So now they ask the conductors will move away or move towards or rotate or remain stationary. Well, this one, right, is related to the magnetic force that one conductor acts on another conductor. So if we call this conductor A, we call this conductor B, right? Because current is flowing in conductor A, that's why there's a magnetic field created by the current in conductor A. Okay, at the same time, conductor B also have current flowing in it. Okay, conductor B has current flowing in it. That's why the current in conductor B will also create another magnetic field also. Okay, just roughly drawing out the situation. So the conductor A over here will interact with the magnetic field produced by conductor B. Okay, conductor A will interact with the magnetic field produced by conductor B. Therefore, conductor A will experience a force that is acted or exerted by conductor B on conductor A. Okay, again, conductor A interacts with the magnetic field produced by conductor B. That because it interacts with the magnetic field produced by conductor B, therefore, conductor A will experience a force that is exerted by conductor B. Okay. On the other hand, conductor B here will interact with the magnetic field produced by conductor A. So this conductor B here will interact with the blue magnetic field over here. Then because it interacts with the magnetic field that is produced by conductor A, therefore, conductor B will experience a force that is exerted by conductor A. So conductor A will exert a force on conductor B, conductor B will exert a force on conductor A. If the force are pointing away from each other, then they will move away from each other. But if the force are pointing towards each other, then they will move towards each other. If the force is pointing not towards, not away, not towards, then they will probably stay the same separation distance. Okay, but if you have torque, then you might rotate. So this thing has been discussed already in the lecture, so I won't go too deep about this. I'll just show the conclusion that we have discussed in the lecture. If you have problem, then feel free to ask, or you feel free to review back the lecture. The idea is if they are flowing in the same direction, if the two currents are flowing in the same direction, they should attract. If they are flowing in the opposite direction, they should repel. So in this situation, they are both flowing in the same direction, they should attract. So they should move towards each other. Okay, I won't go too deep over the concept. For the concept, you can review back the lecture video. But this is the conclusion that we arrive at. Same direction of current, then they will attract. Opposite direction of current, then they will repel. So attract means by the force are pointing towards each other, therefore they will move towards each other. Okay, so that's it for this question. Let's move on to the next one. Question 30. The figure shows three long straight parallel wires PQR normal to the plane of the page. So your page or your screen right now will be the plane that we have. Okay, your screen is the plane and you have three long straight parallel wires PQR that are perpendicular to the plane. So if you look at the diagram over here, PQR over here are actually wires. Okay, but these wires here have current, and in this case wire Q here, the current is flowing towards you, it's pointing out the page. But for wire R over here, the current is pointing into the page, it's flowing into the screen right now. And for wire P over here, the current is also, I think wire P here, there's current on. Wire P carries current that is directed into the page. So your wire P here also have current that is flowing into the screen. Okay, so P and R, the wire is flowing into the screen. Q, the current is flowing out from the screen. Okay, so all three currents are of the same magnitude. So P, Q, R, all, let's say if they have 5 ampere, then all of them have 5 ampere. Okay, which arrow shows correctly the direction of the resultant force on wire P? Okay, so wire P, they are interested in the force exerted on wire P. So you know that there are two forces that are exerted on wire P. One will be the force exerted by wire Q on wire P. One will be the force exerted by wire R on wire P. So there'll be two forces acting on wire P. Let's try to determine its direction. Okay, you know that it's the same thing as just now. If the current is flowing in the same direction, they attract. If they're flowing in opposite direction, they repel. So between P and Q over here, you can see that Q is flowing out of the page. P is flowing into the page. So one is out of the page, one is into the page. So that means that they are flowing in opposite direction. If they are flowing in opposite direction, you should expect their force to be pointing away from each other. So if you draw the force should be pointing away from each other. So this is the force exerted by P on Q. This is the force that is exerted by Q on P. Okay, next we move on to another pair between P and R. Between P and R, both of them are pointing into the page. That means that the current are both flowing in the same direction into the page. Therefore, you should expect an attraction between wire P and wire R. Attraction means by the force will be pointing towards each other. Therefore, if I use another color to represent it, the force here will be exerted by R on P. Okay, on the other hand, this will be a force exerted by P on R. Okay, but now they are only interested with the force exerted on wire P, and they ask for the resultant force. That means you need to merge together, or you need to do a vector sum of the green arrow and the purple arrow. So adding up green arrow and purple arrow, you know that the direction of the resultant force should be pointing in the first quadrant. That's why your answer will be C. Okay, there's also another pair over here that I haven't investigated. Q and R is also another pair. So if we insist on finding its direction, Q and R, they are flowing in opposite directions, so they should repel. So because they should repel, so this should be pointing towards here. This will be the force exerted by R on Q, pointing away from each other. This will be the force exerted by Q on R. Okay, so this is the whole forces acting on each other diagram, but we are only interested with the force exerted on wire P. So merging together force exerted by R on P and force exerted by Q on P, merging these two forces together using vector sum, you know that the resultant vector is pointing in the first quadrant, and the answer is therefore C. Okay, so that's how you solve question 30 over here. Oh, okay, so that's all the question that you all requested me to discuss. So that's it for revision quiz chapter 4.